T2 star, T1, and proton density contrast. Let's get started with some pull everywhere questions. Go ahead and pause the video and answer them. I'll go over the answers after I cover the relevant sections. Before we talk about T2 star contrast, let's revisit the definition of T2 star. T2 star is the time constant which describes how quickly we lose transverse magnetization after we turn off the radio frequency coil. Why do we turn on the radio frequency coil? To review, we turn on the radio frequency coil because we need to rotate M, the patient's magnetism, the net magnetization vector. We need to rotate M so that it's in the transverse plane and separate from B0. If we didn't do that, B0 would overwhelm M and we wouldn't be able to measure it. So when we rotate M into the transverse plane, we deposit energy into it. We put it into a higher energy state, such that when we turn off the radio frequency coil, what happens is that the net magnetization vector, M, wants to go back to its original lower energy state, parallel to B0 in the longitudinal plane. Transverse magnetization is going to start at 100% after we've rotated it into the transverse plane. That makes sense? And when it decays to 37% of that maximum, that time period to go from 100% to 37%, that is T2 star. So it's the time constant which describes how quickly we lose transverse magnetization after we turn off the radio frequency coil. And it's typically on the order of milliseconds. So T2 star contrast refers to tissue differences that result from their different T2 star properties. Remember, tissue contrast is just signal differences in tissues that allows us to distinguish them. So if tissues have different T2 star properties, theoretically we should be able to tell them apart on a T2 star weighted image. So what we're going to talk about now is how do we generate a T2 star weighted image? So let's consider two tissues, cerebrospinal fluid and white matter. We'll notice that the cerebrospinal fluid has a longer T2 star. It holds on to its transverse magnetization longer. And the reason is because, well, fluids tend to have longer T2 star values than solid tissues. That's the intuition I want to build. So it should make sense that cerebrospinal fluid, which is a fluid, is going to have a longer T2 star than white matter, which is more solid. Okay. So if we want to sample the signal associated with cerebrospinal fluid and white matter, and we're just trying to maximize the signal from them, where would we want to sample the signal? Immediately after the 90-degree radio frequency pulse? Somewhere in the middle? Or way out here at the end? So if we're just trying to maximize signal, we're going to want to sample immediately after the 90-degree radio frequency pulse, because the longer we wait, the less signal we're going to have. So if we're just trying to maximize signal, we would sample it immediately after the 90-degree radio frequency pulse. But would that generate any tissue contrast? No. Signal would be maximized in both, and assuming they have the same proton density, the signal would be identical. So what we need to do is we need to wait a relatively long period of time, relative to where signal is maximized, in order to generate T2 star contrast, to take advantages of this difference in how CSF loses its transverse magnetization compared to how white matter loses its transverse magnetization. So I drew this out. Whoops. So I'm going to introduce a new term, TE, time to echo. Time to echo, or TE, refers to the time after the 90-degree radio frequency pulse when we sample our signal. So to generate T2 star contrast, to create a T2 star weighted image, what we need to do is sample our signal a relatively long period of time after where we would maximize the signal. So again, to maximize the signal, we would want to sample it immediately after the 90-degree radio frequency pulse. But if we did that, both the white matter and the CSF would be white, and we couldn't tell them apart. So we wait a relatively long period of time where these curves are going to separate, so that now the CSF is going to be much brighter than the white matter. And I should point out briefly, we talked about dark protons in the earlier part of this lecture when we were talking about tissues that have intermediate density on proton density weighted images. We said that some of those protons associated with macromolecules did not generate detectable signal, and so they're considered dark protons. The reason is because those protons are so rigid, they're so tightly bound that their T2 star is so short that we can't detect them. So if you're wondering about why the protons are dark, that's part of it. Okay, so let's go to the question. So which MR sequence parameter generates T2 star contrast? So answer choice A, B, C, and D are all wrong because longitudinal magnetization recovery, transverse magnetization loss, this is not an MR sequence parameter. We can't control this. These are properties of tissues, how quickly they recover their longitudinal magnetization after we turn off the RF coil, or how quickly they lose their transverse magnetization. That's a tissue property. So answer choices A through D are all wrong. So let's look at the rest of the answer choices. So short TR, long TR, we haven't defined repetition time yet, so it can't be those. So we have short TE and long TE. So remember, to generate T2 star contrast, we wait a relatively long period of time relative to where a signal is maximized in order to sample the signal. Because if we just had a very short TE, these curves haven't separated yet, and we're not introducing any contrast, any signal differences. So that's long TE. And when we're talking about T2 star, the tissue characteristic, we're talking about loss of transverse magnetization. So just to burn it into your brain, long TE, T2 star, transverse magnetization. Okay, those three concepts should be associated in your mind. Loss of transverse magnetization. Okay. So we already did that. We're going to talk about T1 contrast. Okay. So let's consider this scenario. We have two tissues, A and B, which have the same T2 star properties and proton density. Proton density, by the way, determines how high up we go when we deliver that 90-degree radio frequency pulse. So if they arrive at the same level here, that assumes that they have the same proton density. So anyways, we can't do that trick that we were talking about earlier where we vary the echo time, because even if we wait a relatively long period of time relative to where a signal is maximized, we're not going to generate any T2 star contrast because the T2 star is the same for both tissues. So that's not going to work. But if we look at their T1 curves, remember T1 describes how quickly a tissue recovers its longitudinal magnetization. And remember, T1 takes a longer period of time than T2 star. We recover longitudinal magnetization more slowly in general compared to how quickly we lose transverse magnetization. It's a different mechanism that governs T1 compared to T2 star. So if we look at the T1 properties of tissue A and tissue B, we see that tissue A is recovering its longitudinal magnetization much more quickly than tissue B. So maybe there's a way that we can take advantage of that in order to distinguish tissue A from B. So indeed, there is a way to do that. The way to do that is to repeat the pulse sequence. So this is an important point. We don't just do the MRI pulse sequence once. We have to repeat it many times in order to generate a meaningful image. And we can actually use this repetition to change the contrast in our image. So I'm going to ask you a question. If we just want to maximize signal, maximize transverse magnetization on our second repetition of this MR sequence, when would we want to put the next 90-degree radio frequency pulse? All the way at the end here, somewhere in the middle, or immediately after the 90-degree radio frequency pulse? If our goal is just to maximize signal. So we would want to put it all the way at the end here, because at that point, all of the longitudinal magnetization has been recovered. And so when we deliver our next 90-degree radio frequency pulse, all of that longitudinal magnetization is going to be able to be converted into transverse magnetization. So this is an important point. We can't generate transverse magnetization signal unless we have longitudinal magnetization to start with. So if we're just concerned about maximizing transverse magnetization on the second repetition, we need to maximize our recovery of longitudinal magnetization. We need to wait until all that longitudinal magnetization is recovered so that we can send it into the transverse plane with the next 90-degree radiofrequency pulse. But if we did that, what would happen? It's not going to have any difference, right? A and B are going to have the same longitudinal magnetization. They're going to decay with the same T2 star. Can't tell them apart. So what we want to do is we want to repeat the pulse sequence somewhere in the middle here where these curves have separated. So I'm going to diagram that out. Oops. So we're going to want to repeat the pulse sequence somewhere here where these T1 curves have separated. And look what happens. When we flip the longitudinal magnetization for tissue A into the transverse plane, it has more longitudinal magnetization to start with, and so it's going to achieve a higher starting transverse magnetization. When we flip the longitudinal magnetization of B into the transverse plane, it doesn't have as much longitudinal magnetization as tissue A, and so it's going to start with less transverse magnetization. So that is the way that we can capture this signal difference in tissues A and B, is because we can't measure the longitudinal magnetization directly. Remember, in the longitudinal plane we have B0, and that prevents us from measuring anything directly in the longitudinal plane. So what we do is we just wait for the longitudinal magnetization of A and B to be different, and once it's different, we flip it into the transverse plane so we can capture that difference. So I'm going to introduce another term, which is TR, repetition time. And that refers to the time between 90-degree radiofrequency pulses. How long do we wait before we repeat the pulse sequence? So far we have two terms for our MR sequence parameters. We have TE, the time after the 90-degree radiofrequency pulse when we sample our signal, and TR, the time between repetitions of that same pulse sequence. So to generate T1 contrast, we need to use a short TR, a short repetition time, relative to where signal is maximized. If we wanted to maximize signal from the next repetition, we would want to wait until all of our longitudinal magnetization was recovered. But that's not going to work here because they have the same T2 star and we wouldn't be able to tell them apart. So we have to use a relatively short repetition time to take advantage of this T1 property differences. We want to separate the T1 curves, and we need a short TR relative to where signal is maximized to do that. Oops. Okay, so we'll come back to gadolinium in a second. So which MR sequence parameter generates T1 contrast? So again, the first four answer choices are wrong. Longitudinal magnetization recovery, transverse magnetization loss. These are tissue properties. We can't control them. They're not MR sequence parameters. T1 contrast is governed by short repetition time, right? Relative to where signal is maximized. So that's why this is the correct answer. And T1 describes how quickly a tissue recovers longitudinal magnetization. T1, longitudinal magnetization. T2 star, transverse magnetization.